Hello everyone, how's everybody today? I hope you're doing fine. Just wanted to go over a little bit of my discussion with JFG the other day. I was on his program again, known as the public space. And I discussed specifically the rope model of light, not only of light, really of light, the atom, gravity, electromagnetism in general, magnetic attraction, electricity. I covered those 5 subjects specifically. And the idea was to argue that as a minimum, the rope should be considered side by side with the other 2 options that we have today, which is the wave and the particle. People say that light is a flow of particles, a series of particles, bullets, one right after another. And others say it's a wave. Some say it's of nothing. Others say it's of the ether. And after 400 years, we have a new proposal, and that's the rope model. And what are we saying? We're saying that light is mediated by rope. And it doesn't go up and down. It's the torsion, 3D torsion. So we have the 2D wave up and down. We have the, I guess, longitudinal particles. That's the way they always draw them, longitudinal waves, kind of, just rarefaction and compression of particles back and forth like sound. And but they say it's a transverse wave, so you figure out how they can reconcile those 2 notions. And then you have the 3D torsion. So we can say 1 longitudinal particle waves, or train of particles. 2, D is the transverse wave, up and down, standing wave. And then we have the 3D torsion of a rope. And I showed that, at least the rope, as it relates to light, can at least answer speed, why light is so fast, why light is a constant, why light travels so straight. Taut rope, the torsion never gets lost, never goes, never curves or anything. It always goes straight along the ropes. And well, several properties of light. And I also showed, even though I didn't dwell too much on it, that the other proposals, wave and particle, they don't meet some of the minimum requirements that we need to cover the specification of light. Light has already been known for the last 200 years to have certain properties. And neither the transverse wave nor the flow of particles model, neither of those 2 really, explains or justifies many of the properties of light. The rope justifies them all. But even if you disagree, you may say, well, I think that the standing wave does mimic certain properties. The particles simulate some other properties. Fine. As a minimum, the rope should be considered side by side as a candidate for as a mediator for light. And that was the main point that I was trying to make. Not only did I cover the light, I covered also the atom. And when I look at a little bit of the atom today, how it relates to that discussion in general. And today I put up a video showing the history of, how the atom, the notion of the atom, of this unseen little thing that makes up everything, how it progressed through the ages. And some of you saw the video, but I'm going to go through it real quickly, just to put everybody in the same on the same page, in the same mind frame. And here it is. We start with Leucippus and Democritus, right? And Democritus essentially came up with the ball. Not that one there, that's today's atom. He came up with a ball, that one. Okay, it's the indivisible ball. In fact, the word atom means indivisible. Okay, and by the way, I put the Parthenon there, but Socrates was not a guy that lived in Athens. But the building looked cute, so I thought it'd serve as a little bit of background there. Anyways, about 400 BC, him and his tutor, I guess, Lucippus, they came up with this notion that there is some kind of indivisible entity out there. They called it the atom. That's the word we have today. And we thought for the next 2,000 years that actually it was an indivisible, that everything was made of these little stones, these round stones, invisible round stones. And that's what we dealt with all the way to the 19th century. 19th century, we have Mr. Dalton specifically, and he came up with this, you could call it a periodic table. 1827, he had an earlier one in 1808. They say he stole the idea from William Higgins, an Irish guy, chemist, who either sued him or at least challenged him and said that he was plagiarized by Dalton. Anyways, this was the model. Again, you can see they're still dealing with spheres. Okay, nothing changed from the days of the Greeks. And essentially, you know, we lasted, you know, then you have Mendeleev. He comes a little after mid-century, 1870s. In fact, he started like 1863 was his first periodic table. And the second one came out 1871, a more complete one based on the atomic weights. And he published in Russian, and so he didn't get a lot of coverage, but then he also published in German. That's where he got a little more well-known, you know. By the way, am I getting feed? You mean back feed? What? Is there a problem with sound again? Martin, is there a problem with the sound again? Please let me know. Oh, okay. Okay, so you had a problem on your side. Okay. Okay, as long as you can hear me, but please let me know if there's something with the sound. I think next time I'm going to try to use a different computer. Okay, I'm going to change the computer, see if that does anything. But anyways, let me continue. Where was I? Dalton, he came up with these, really he had the same spheres as his predecessors. So they just realized that every atom has a different sphere. And you can see the little drawings here for Dalton. You know, it's like he just put little signs in them. He didn't understand. He just says they're all spheres, but somehow I got to distinguish them. And he just drew these symbols to distinguish one particle from another. Okay, and it would not be until Mendeleev, after mid 19th century, that he comes up with a periodic table. And until he published in German, he was not really well known. But after that, his table was accepted worldwide by chemists and physicists. And it was based on atomic weights. And that's the table we have today, much more improved with more elements that have been found since then. And, well, you know, that's the rest is history, as they say, okay? Okay, beginning of the 20th century, we have Mr. J.J. Thomson. And he had the plum pudding model. Here we have a fluid inside a ball. That's how he envisioned it. That's how he described it. He says he thought it was like a fluid, and and it's a positive fluid for some reason. and he's got these negative charges just floating in there. Okay. Same year, 1904, we have Mr. Hantaro Nagaoka, and he comes up with the Saturnian model, which is pretty much like, if you come to think of it, right, it's pretty much like the planetary model. So it's not like, you know, the people in the West came up with a planetary model first. This is in some way a planetary model, except that what Nagaoka was saying was that, you know, all these negative charges, they orbited around a plane. So he imagined it like Saturn. That's what's called the Saturnian model. And this is going to come in somewhat handy to Mr. de Broglie in 1924 when he comes up with his wave, that the electron is a wave that surrounds the middle of the proton, or the middle of the nucleus, and like a hula hoop. And you can see that where he could have gotten the idea. He probably got it also from Nagaoka. Okay, so this model was still around in those days. It's just not so famous in the West. Okay, it's not so well known here. Rutherford and his team, together with Marsden and Geiger, guy who invented the Geiger counter, they developed in 1911. By 1911, they started like in 1908. And they developed this atom, which is the same thing as Nagaoka proposed, except that the electron does not orbit in a given plane like the rings of Saturn, but instead it just goes all over the place. Okay. And Niels Bohr, then a couple years later, who was working also at the same lab as Rutherford, he comes up with his famous atom, in which he explains why the, essentially he explains what is known as quantum jump or quantum leap, which is that the electron falls to a lower energy level and rises to an energy level, and by doing so, by going back and forth within these two levels, it releases and absorbs packets of energy. The packets of energy that were discovered a few years earlier, or theorized a few years earlier by Max Planck, actually 1900, turn of the century. He said that light comes in discrete packets. And you know, essentially Niels Bohr incorporated that notion within his model. And by the way, Einstein also incorporated in his analysis of the photoelectric effect. You know, that quantum became very famous because, according to all these people, it could explain a lot of things, but it forced them to assume that light really consisted or came in packages, in bundles, in discrete stones, okay, so to speak. Okay, we have 1924, we have Mr. Louis de Broglie, and he comes up with his wave model. He says the electron is really a wave. I guess he imagined it as a two-dimensional wave because, you know, we cannot imagine what will come later, which is the shell, which is the cloud model. So this one is a 2D wave. He just described it mathematically, and essentially the electron bead, because he can't get rid of the bead. The bead jumps from one energy level to another, which is what Bohr had already said. But he says, you know, the electron is really spread out. It's kind of like, it's not a little ball, but it's really the wave itself. It's a wave that goes in integral or in integers around, you know, the atom. There's no half integer. You don't get 10 waves and a half, or 10 what is it, 10 yeah, I guess you call them waves. Each one of those lumps there, or two of them, I guess, or what, it would be half. Yeah, from the top of one to the bottom of the other, that's what it would be. Well, one of those, we'll call it a wave, and you need to have integer numbers of them. You can have 10, you can have 11, but you can't have 10 and a half. That's what Louis de Broglie calculated, and he came up with the equation, got a Nobel for it, right? And so that's the model that was accepted up to that point regarding the electron. And the last one to come out, and the one we use today, and that's Schrodinger's and Born's cloud model. They're saying, well, it's not really a particle, it's not really a wave. What it is, it's a cloud that encapsulates the nucleus. When it shrinks and expands, it releases energy. That's what those those lightning bolts are, okay, going out of there. And you should have a couple coming in as well, because it absorbs and emits, okay. And so this is the model that we had and that we have today. This is the model that you're taught at the high levels of the university, as you can see, and nobody likes to illustrate it because they don't believe that this is correct either. In fact, they don't use this model, and that's important to note. You know, they don't really use the Born model. I'll call it the Born or the Schrodinger model. They don't use it because when you explain electricity, when you explain ionization, you know, you go back to the planetary model, to Bohr's or Rutherford's model, where you have the nucleus and the little bead. And the bead goes from atom to atom. That's electricity for you. And if you pull the bead from the atom, you've got ionization. You know, there's no mention of orbitals, of clouds, of shells at that point, in that context. The shell is brought in when you're doing covalent bonding. You know, two atoms come together, and depending on which atoms, right? You can have ionic bonding, you have metallic bonding, you have hydrogen bonding. You know, you got all these different types of bonding. Covalent bonding is the merging of shells. So they get rid of the bead, and they say, look, physically what's happening is the shells merge, but there are no shells. See, the shells is a region where you can find the electron bead. We get rid of the bead, now we only have the region. Now the regions are coming together. Now we're reifying the regions. We're saying the region is now a shell, and we're going to get two shells together, merge them, you know, blend them together. That's what they're saying. So yeah, that's the idea that we have today. What does Bill Gates come up with? Well, I'm saying that, you know, these people have been mistaken all these years. This is what we have. We have our dear atom here, showing how it's constructed. We're going to construct a proton star and the electron shell, which encapsulates it. It pumps there and creates light. And here's how it's constructed. You have the electric thread going through the middle, and you have the magnetic thread going around. And electric and magnetic are just to stick with convention. And what happens? You have that model there where one encapsulates the other, and when it pumps back and forth, right, it torques the rope. And by torquing the rope, what we're doing is essentially sending light to, you know, to the rest of the universe. Okay. And just in case, I've got something some people sometimes want to see it. And here's how an atom, we have an atom here, we'll call it a hydrogen atom, just approaching another hydrogen atom. Maybe they're going to convert into hydrogen gas, H2. And what we have is they're pumping at each other, right? And then what it does is it slides along the rope. Okay, one is going to slide along the rope, and it's going to eat links as it goes forward and release links behind it. And that's when I say, you know, that an atom slides like a bead on an abacus. That's what I mean. That's the mechanism there. Okay. Okay. So that gives you an overview of the atom, and that's the overview I wanted to give JFG on Wednesday when I talked about it. He raised the question, and it's a question that a lot of people ask themselves, and it's got to do with, just in case, checking to see if the sound is okay. It's got to do with what is known as light on light. And the issue has to do with whether the ropes, in the case of light on light as it relates to ropes, whether the ropes cross each other or not. Because, people immediately ask, well, so many ropes in the universe, every atom is interconnected by ropes. Do these ropes go through each other at any point? And I call it the tangling issue. It's known in official circles as light on light. Either term is essentially a synonym. It relates to this problem. And all I can tell you, it's the number one problem, the only problem we need to solve. It's the only problem. It's a headache of a problem, believe me. I spent 2 years on it, and I'm not bragging. I'm just giving you a fact. It's a monster. And so the question is, what kind of answers do we have for this? And I told JFG, I gave him the answer. I gave him, really, I said I had a series of answers, 3 or 4. And I want to go through them because, I want people to understand what the answer is. Okay, here goes. Here's the first argument. The first argument, these are the arguments. One is that it's a premature question. Premature question. And you might say, Bill, what the hell do you mean by that? What do you mean it's a premature question? Yeah, it's a premature question because I presented with JFG, but it can occur with anyone out there. You explain the theory and you say, look, this is the model that I'm going to use and these are the theories. This is how I explain magnetism. This is how I explain light. This is how I explain gravity, etc., etc. And the workings of the atom as I just showed you a second ago, how the atom is constructed, how it pumps what is known as, quantum jump. It's a different model. We have a balloon going back and forth, torquing the rope, light goes along the rope to another atom. So once you explain that, the person says, well, you got all these ropes, what are they made out of, they say. Answer to that one is easy. It's made out of 2 threads, 2 twined threads, so that's an easy question. And and that takes them off guard, and they say, well, what are the threads, man? They want to continue, So I have a lot of fun with that one. But let's get back to this one, the tangling issue, the light on light issue. Okay, the first one is that the first answer to that question is a premature question. Why? Because here I've showed you that light, that the rope can simulate magnetism, and let me show that just real quickly, just for the hell of it. Let me see where it's at. Here it is. Give me a second here till I get the thing here. Here it is. This is what we have to explain. We have to explain those patterns that the magnetic field, so-called magnetic field, leaves around a magnet. And we know about these patterns because we drop iron filings around them, and we know that the flow of the lines of force move like you're seeing there. You're seeing that it goes in on the inside. Where it goes in, that's the south side, and where it goes out is the north side, okay? And we have to explain these patterns. And the rope model explains them. It says, look, one of the threads comes loose, goes around the atom, okay, and through the center and out the other end. That's what's happening with a thread. So we have to look at the thread as a physical entity. It goes through the center, and then how does it produce attraction? Here, you'll see it in the next little piece here. At the bottom, you see how they latch on the left and how they push each other away on the right. So we do have a mechanism. Now, it doesn't mean you have to buy this mechanism. What I'm saying is, we have a mechanism. We're showing, look, with a thread, with a rope, one of the threads comes loose, or 2 threads come loose, it doesn't really matter, and it goes around the magnet. And by doing so, first we can explain the patterns left on iron filings. Second, we can explain how they push each other away, or if they both go in the same direction, here it comes down, here it goes up, we can explain attraction. So we have a mechanism. You don't have to agree, but we do have a mechanism, And so that's the important part. We have a mechanism with a rope. We also can explain light. We're saying, okay, how about light? Okay, how do we explain light? Here we have the checklist of light, which I showed. Give me a second here so I get this thing up there. Here's the checklist of light. Any entity that has to simulate light must meet these specifications. It has to be a body, it has to be an object. You can't say it's the waving of nothing, as quantum says today. It has to start at the atom. You know, light does start at an atom. In fact, I think I have something to show for that. Let's see, do I have that? Somewhere I do. Yeah, here it is. Just for those who, because JFG asked that question, does it start at an atom? Here it is. Yeah, the atom pumps back and forth and generates, in the case of quantum mechanics, generates those photons, those balls, which travel outwards, okay? So the quantum jumping generates light, and that means that light starts at an atom. Light does not get generated in heaven by God. It gets generated by the pumping of the atom somehow. You know, the little bead electron bead goes back and forth, somehow creates energy, and that energy is light. Okay, it's travel. Whatever we propose for light has to travel rectilinearly, or in my case, stretches straight. It has to travel very fast, and you have to show why it travels at 300,000 kilometers per second, why it's a constant, and it has to meet all the wave properties. It's got to have, you know, it should oscillate around an axis, because that's what the electromagnetic wave, the transverse wave does. Faraday-Maxwell laws, the magnetic field generates the electric field and vice versa. They both travel perpendicular to each other. And then it has to have the features that include frequency, wavelength, and amplitude. Well, right there and then, these wave properties eliminate the particle. You can't have particles, okay? Because particles cannot explain why it goes up and down, frequency, wavelength, cannot explain any of these features. If anything, maybe you can make a case of the ones on the left, but not the ones on the right. So, you know, does the rope answer these questions? And the answer is yes. The rope is straight, it's pulled tight, you know, it's fast. In fact, I made the case that, where is it? Here it is. Here's the comparison. We have the transverse wave that's used by mathematical physics. Which is the snail there. We have the turtle, which is the longitudinal wave, which is always compared against it. And what these people forgot is the torsion wave. In other words, if you have a torsion along a rope, it not only travels much faster than the other two, in fact, it's the fastest thing known to man, but it travels in both directions. And it travels straight. It can't do it otherwise because the rope is pulled taut. So, you know, again, it doesn't mean you have to agree with any of this. All I'm saying is that the rope has an explanation, has a justification for some of these properties. It can do magnetism, two magnets, we can show that. It can show some of the properties of light, in fact, all of them, as far as I'm concerned. I showed electricity. I'm not going to go into the details here. I showed gravity. You know, you have, let's see if I can show just the picture that summarizes, I think it's this one. Well, yeah, here it is. It's this one here. So here's gravity for you with ropes. We have an elephant falling to earth, and the ropes, every rope is tight. Remember, it's pulled tight, so all the ropes are straight at all moments. There never does it bend. And here you have it's interconnected ropes versus discrete particles. All the atoms are interconnected from one object to another. As one object approaches another, the ropes fan out. Okay, that's the mechanism. And so when the elephant falls to earth, you can see that more and more ropes fan out and tug or act independently. Okay, once again, you do not have to agree with any of this. All I'm saying is, with a rope, we can do light. With a rope, we can do magnetism. With a rope, we can do gravity, electricity, the atom, you know. So with just this model, we can do all these things. We meet the fundamental requirements of each one of these. We meet the specifications. And if that's the case, the argument again is, you know, as a minimum, it should be considered side by side with a particle and with a wave. That's all I'm saying. I think it deserves attention from that point of view. And so it's a premature question to ask, what is the rope made out of? Or what does the rope cross? Do ropes tangle, or do they cross each other, etc.? If the rope doesn't qualify, if the rope does not answer light, if the rope does not answer magnetism, if you believe that the rope does not answer gravity, then we don't need to get to that other step. See, first we have to answer these other questions. Does the rope explain the mechanism of attraction, the magnetism? Does it explain the attraction according to gravity? Does it explain the properties of light? If you say it doesn't, then I'm not even going to need, I don't even need to answer the question of, you know, what is the rope made out of? Does it stretch from here to Andromeda, from one atom here to an atom there? Do they cross each other? Those are irrelevant questions, because you've already decided that it does not answer the mechanisms that we know for light, gravity, magnetic attraction, electricity. That's the purpose of the rope. The rope is going to be used to answer these questions. And if you're saying that you don't agree, then what's the point of asking if ropes go through each other? Okay, so it's a premature question in that sense. You either buy into the rope and then ask these questions, but first you got to concede that the rope does explain the mechanism. And if so, that means that it should be treated side by side with a particle in the wave, period. Whether you like it or not. Now, once you concede that, then we can talk about, you know, properties of the rope, whether it crosses one another or not, okay? Or what it's made out of, that kind of thing. The first question, does it explain mechanisms? That's the first question, must be answered. In that sense, any question outside of that is premature. Okay, so that's the first one. Here's the second one. If we reject the rope, we got to go back to quantum. We got to, or classical, whichever. In other words, we got to go back and say, okay, we're not going to accept the rope. We got to go back to particles. We got to go back to waves. That's all we got. Because in the last 400 years, we've only had three proposals on the table. Now, some people say, well, that's not true, Bill. We have vortices, we have ether, you know, we have all these goodies out there, the field, you know. And, you know, again, these are not objects. And it takes a long time for people to understand that. Plasma, you know, electricity, these are not physical objects. And it takes 2 years for these people to understand that. You gotta really talk to them a lot and the guy to put some interest. They think you're just doing semantics. Whether I'm going back on JFG's show, not this week. I don't know. I have no new schedule with him. He might call me back, Martin, so I don't know as far as today's concerned. I don't know. I don't have any plans from that angle, okay? Anyways, the point here is that the second issue we must answer is that, here I got lost a little bit here. Let me put it back. That if we don't do the rope, if we don't accept the rope, we got to go back to particles, and that's a problem. That's a problem because particles don't answer any question. And one of the main questions that particles don't answer is this one here, the one that troubles people so much. Let's see if I can find it here. Well, here's the three models. These are the three models proposed. We have the standing wave or transverse wave, whichever one you want there. You have the discrete photons, particles, corpuscles, and we have the torsion. Those are the three, okay? And there are no other proposals on the table. So we don't take the rope. We got to go back to one of those. And what can it answer? Oh, here's where I wanted it. The second one, the third one there, quantum superposition decoherence. See, the issue we've got here is that quantum also has a tangling problem, or has a problem with light on light. And the issue is that they call it superposition, that two particles can be at the same place at the same time. And so people say, well, Bill, do the ropes tangle? And I answer, well, why didn't you ask that question to the quantum mechanics guys? I mean, when they say superposition, they're saying two particles occupy the same space, and they don't bump each other out like normal things here in the macro world do. And you never asked the question. They just said superposition, you say, uh-huh. Or they say something worse. To explain the slit experiment, they say the particle can be at two places at once. It's not that the particle breaks up in two. The same particle is at two places at once. Nobody asks these questions. It doesn't affect anyone. Everybody's okay with all this stuff. So we've got a problem. We've got a problem when people ask the question from the rope. They want to, put the rope on trial and say, oh, I'm going to question you to death. Why don't you question quantum mechanics first? Because they have a tangling issue also. They just call it superposition, and you never called it out to them. You never called their bluff. It's like, oh yeah, superposition, oh, decoherence, particle can be at two places at one, no problem. At least the rope doesn't say the rope can be at two places at once. But, the tangling issue is a valid issue. Again, I broke my head 2 years on it. I know how I'm an expert on that. Let me tell you, I broke my head on the tangling issue. But before we answer that question, let's tackle quantum. Let's make sure quantum dies so we don't go back to quantum. Okay? So first let's talk about superposition. Let's talk about decoherence. And then we'll answer all the questions you want about the rope. Let's make sure quantum dies. If quantum can't answer it, I don't have to answer it. That's what I can say. That's what I can argue. First, fix the official version of the atom. First, fix the official version of light, of magnetism, of electricity. First, let's destroy that so we don't go back. Let's burn that bridge so we don't cross backwards. Okay, what's another argument? Another argument is that in order, which I mentioned to JFG, is that in order to understand an explanation, you must set the foundations. You must plant the foundations of physics. You must make sure that people understand the language of physics, understand what physics is about. And like I told them, the first things that you need to establish are you can't do physics without an object. Imagine, you raise everything out of the universe. God comes in, just wipes everything out, leaves nothing, whatever nothing means to you. There's nothing there. Okay? What's happening? What are you observing? What experiments can you do with nothing? Obviously, you need to have something. We'll call those somethings objects. Okay? We'll call them objects. So you need an object to do physics. You can't do physics without objects. And if that's the case, you need to define the word object. You need to know what an object is for the purposes of physics, and nobody has done so in the last 10,000 years. Not a single book of physics begins by defining the word object or telling us the importance that you can't do physics without object, because if they would start with that, then people would understand why it's important. But people don't even understand how important it is to define the word object and why you need to define the word object. And that's not the only word. You need to define distance, location. What is motion? What do you mean by exist? Physics is the science of existence. So you need to define these terms so that you set the foundations for physics. And people want to skip all that, and they say, well, no, I don't want to deal with grammar or semantics. I want to do physics. No, you need to eat your soup, okay? Become strong. So you can't do physics unless you understand the language, unless you understand what the purpose of physics is. And you can't, people want to go to college and talk about, how the ropes avoid tangling. And they don't want to go through kindergarten to learn the foundations. That's the issue. Because they say, well, that's not physics, that's grammar, that's semantics. Now you need to. And so if besides you need to in order to understand my answer, like I gave the example of the word touch. Before ropes can cut across each other, or I gave him the example. I like that example because you got a rope, right? And you have a pair of scissors. You're going to cut through them. Before you can cut the rope, you need to touch the rope. The blades need to touch the rope. And so the question is, what do we mean by touch? Everybody said, what kind of question is that? Everybody knows what touch means. Well, yeah, in ordinary speech, we say we touch the table, but in scientific language, in physics, you need to define what the word touch is because it's going to make or break your theory. Did the scissor touch, did the pair of scissors touch, the rope before it cut across? And, again, we have that issue where touch means, zero distance between two objects. But zero distance means they convert it into one object, and that destroys the definition of touch, which requires two objects and distance. And so, as long as you got space between the two fingers, they haven't touched each other. And I squeeze on, and I still haven't touched them because there's always space between the two fingers. The atoms did not blend. Proton did not come against proton in there. And so we go back to the word touch. And all I'm saying is, you need to define these terms before you can deal with issues like, does a rope avoid tangling? Does it cut across? What does a rope do? There's a lot of issues to be resolved. This is not a simple question, okay? And again, one of the things I have is that I don't deal with the tangling issue on the internet. I've said that times in the past. I say it one more time officially. I do not answer questions regarding touch, regarding tangling, or touch really for that matter. But I don't deal with the issue of tangling with light on light because 99% of the people out there, they don't have the right language to understand physics. We got bigger problems, more basic problems. These people want this high-level question answered. This is the problem. And so they get it all wrong. They always get it wrong, and I'm just wasting my time trying to explain it to them. So I don't do that. What I'm saying is, you want to know whether they avoid tangling, whether they tangle, whether they go through each other or not. Chapter 7 of my book. And they say, oh, that's just a way of selling your book. That's not the point. The point I'm trying to make is I have an answer. I've written it down. It's published. It's there. Okay? The answer is there. I'm not going to deal with it on the internet because people don't have the right language to understand my answer. Okay? You need to eat a lot of soup. You need to really get a lot of words really deep in your head to understand the language first so that you can understand the question and the answer. Okay? So there's a lot involved with the tangling light on light issue. Okay, and among those issues, one of the very important issues is whether light touches light. You have two lasers, okay? You point them at each other. Do the photons, waves, whatever, ricochet, bounce, and come apart? So we have a couple studies. One of them is by Mr. Burke, okay? And his team came up with this paper, okay? Positron production and multi-photon light-by-light scattering, okay? And according to Mr. Burke, yeah, particles of light bounce off each other. It says the positrons are interpreted as arising from a two-step process in which laser photons are backscattered. Laser photons are backscattered. They bounce off each other and, by the electron beam followed by a collision between high-energy photon and several laser photons to produce an electron-positron pair. Okay, later on he uses the term virtual photon to refer to that. So virtual photon enters his discussion. And when you look at some of these key terms like the Weizsäcker Williams approximation, you find out that, in that case, the electron carries a whole bunch of virtual photons in a knapsack and unloads them at will, so that the mathematician doesn't have to justify that. Essentially, you got infinite photons there, and so they don't have to count them or anything. You don't have to worry about that. And then a virtual photon is, you look it up, and it's a particle-like abstraction, which facilitates understanding of calculations. The term is rather loose and vaguely defined. They appear in calculations, but never as indexes to the scattering matrix. They never appear as the observable inputs or outputs of the physical process being modeled. Their existence is questionable. However, the term is useful in informal, casual conversation or in rendering concepts into layman's terms. So, that's what a virtual photon or particle is. So here we have Mr. Burke, and he writes a scientific paper allegedly, and he's using words, terms, virtual photons. That's how he explains it, which is from ordinary speech, which is an abstraction, which would not be included under scientific language. And it turns out he claims that photons bounce off each other. When you push them against the ropes, he said, well, they're virtual photons. What are the virtual photons? Well, I created at will from my magic wand. So that's the story for the virtual photon. So the bottom line, do photons really bounce off each other? I mean, here you have, let's see if I can put a little video to show you what the problem is. Here you have two sprays, okay? And again, the question goes to light on light, whether photons bounce off each other. And the question is, do particles of light collide? Well, Burke says they do, but he uses the virtual photon to explain it. Now, we know that macro particles, like in that spray there, we know those bounce off each other. You don't have to take my word for it. Just take your shower head and point it against another shower head, and you'll see that some of the particles bounce off each other. You know, if you point them fast enough, they'll bounce and they'll splatter and they'll hit each other because there's something there, okay? But when you do that with two lasers, you don't see the little photons bouncing off. And what Burke tried to do here was show us that, yeah, indeed, they do bounce off each other, okay? They bounce off each other, ricochet, and go backwards. And so this issue is quite fascinating, because we have Mr. Rutherford, and he ran an experiment in 1911, and it went something like this. He threw alpha particles at a thin gold foil, right? And the particles went through most of them, but one of them, or a few of them, very few of them, bounced back from the gold foil. And he came up with the idea that because of this, that an atom was mostly empty space. That's why most of the particles went through. And the ones that bounced backwards were because they hit the proton. That's how he came up with the idea that atoms have a nucleus in them, and that nucleus is governed by a proton. Okay, so if these particles bounce back, well, then you can say, well, maybe photons also bounce backwards. But see, we got a problem, because if Rutherford reached the wrong conclusion. He concluded that an atom is mostly empty space because the alpha particles, he also did it with beta particles, by the way. Let me just show that real quick, what I'm talking about. Alpha particles and beta particles, that's what they are. An alpha particle is essentially a helium atom, 2 protons and 2 neutrons. And a beta particle is just either an electron or a positron, a positive electron, okay? So beta particles are smaller than the alpha particles, first of all. And second, you can say that the alpha particle is matter, but the beta particle is, well, yeah, I guess an electron is matter when it's a particle, not when it's a wave. Okay, so that's essentially what Rutherford did. He just threw these particles at a gold foil and found out some of them bounced, but most of them went through. And so he said, well, if most of them go through and only a few bounce back, the ones that bounce back hit the proton, the center, the nut right at the center. But all the others went through because an atom is mostly empty space. That was his conclusion. And of course, chapter 7, you have a different explanation for the same phenomenon, for backscattering, and it shows that an atom is not mostly empty space. It just has properties which Mr. Rutherford, who just dealt with particles, did not consider in his evaluation. So it's a long story, but all I'm saying, there is a different explanation for the same phenomenon that Rutherford explained, and the rope model does offer this alternative. Okay, and again, it's a long story. I'm not going to deal with it here. It's outside the the context of the context that I'm trying to explain right now. The other thing is, if we go back to particles, we've got the problem with a water sprinkler, the water sprinkler version of light. If a photon is released by the electron jumping back and forth between energy levels, if it releases a photon, well, and a photon is a discrete particles, none of those particles should travel straight. Okay, they should all travel in curves. Like here you have, they should travel like a water sprinkler. They're showing, like the drops coming out of a water sprinkler. Here you have the sun, and the sun emits photons. And every atom in the sun emits a photon. And let's look at just a single atom in the sun. It emits one photon. The atom is spinning, and so is the sun. The sun is constantly spinning. So the next photon will travel not right behind, right behind the other one in a straight line. It'll travel in a curve like a water sprinkler. It'll travel, like I just showed a second ago. It'll travel more or less like this. Okay, because if the sun is twirling around, all those water droplets, they're not going to go in a straight line, not the ones coming out of one of the nozzles, for example. And here we have, photons coming out of one atom, they cannot travel straight. And so, the particle model cannot explain the straightness of, or the rectilinear propagation of light. Cannot explain that, okay? Let's see, Martin, did you ever get to provide an answer in person to that other inmate who asked you to prove the non-existent existence of God? Oh, what, you got started in your quest? Yeah, no, I never got to answer that question. I just got sidetracked by physics at that point, never came back to religion again. With the traditional religion. I got into a different religion called mathematical physics. So, no, I never went back. The answer really to the question is the one I had given them, and that is that, the person who proposes God, he's the guy giving the presentation. He's the guy with a microphone. He's supposed to tell us that what God is, and second, why he exists. He cannot say, well, here I am, I propose God, prove to me, I'm the speaker, I'm the guy giving the presentation, prove to me that my God doesn't exist. No, you're the guy who has to make his case. You're the prosecutor of the theory. You're not the defendant, you're the prosecutor. You're the guy who's supposed to prosecute your theory. You're supposed to go out there and try to convince people, or explain to them at least, your logic, your rationale. You can't later on say, well, I'm going to say that angels exist. Prove to me that angels don't exist. I say that spirits exist. Prove to me that spirits don't exist. I say that space-time exists. Prove to me that space-time does not exist. It doesn't work that way. And that's essentially the answer to God. So that's the answer I had given them. I've never looked back. That is the correct answer, I think. There's no other answer for that. The guy who gave them the presentation must justify his assumptions. You don't go out there and say, because see, the way it works is you say, let us assume that God exists. Okay, no problem. Let us assume, so I can understand the theory. And he says, God is this man with a magic wand. Fine, no problem. And let us assume he exists. No problem. You can't at the end of your presentation just say, well, prove to me that my God doesn't exist. Well, I don't prove because it's an assumption. We conceded the assumption to understand the theory. That's the mechanism. That's how the scientific method works. You provide an assumption so that the person understands the theory that you're going to explain with that assumption. You can't later on at the end, as part of your conclusion, say, prove to me that my assumption is, doesn't exist. My objects don't exist. It doesn't work that way. Anyways, the point that I'm trying to make that, the rope can explain or justify many of the properties of light, magnetism, electricity, the atom, and the workings of the atom, and also of gravity. And it can do all of these, where the wave and the particle cannot. But let's forget about that. All I'm saying, the soft conclusion, as I called it, the mild conclusion is the rope should be considered side by side with these other mechanisms or objects. Okay? And with that, I'll see you next time, same station. We'll see you then. Bye-bye.